In this video, let's see how to configure HSRP. And we're going to use this topology we were talking about in the previous video where we've got SW2 and SW3 as multi-layer switches, but they're going to be configured for HSRP. And we want switch SW2 to be the active HSRP router for this topology. And the virtual IP address that we're going to be servicing is 10.1.1.1. Let's get started on SW2 by going into interface configuration mode for Fast Ethernet 0/3. That's the interface that's part of that subnet that we're servicing with HSRP. You see it's already got an IP address of 10.1.1.2. And with HSRP, we're not going to use the IP address of an interface as the virtual IP address. By the way, we can do that with VRRP, but we're not going to do that with HSRP. Instead, I need to educate this interface about the virtual IP address that it's servicing. I'm going to say standby, and I give the HSRP group number. I'm going to say group 10. We can have more than one group, remember. That can give us some load balancing. We'll say standby 10. I want to service an IP address of 10.1.1.1. And the default HSRP priority is 100, and higher is better. And I want this to be the active router. And as a result, I'm going to set this to a higher priority value. I'll say standby 10, priority, let's say 110. And if I were to lose my role as the active router, maybe an interface went down but came back up, or the router rebooted. If I lose for whatever reason my active role, but then the condition that caused me to lose that active role was fixed, it got repaired, I'm ready to become the active router again, I want to reclaim my active role, and to make that happen, I need to say standby 10 preempt. And I'm done with my initial configuration on SW2. Let's go to SW3 and set up a similar configuration. On SW3, I'm going to go into interface Fast Ethernet 0/3, and I'm going to give the same virtual IP address and the same HSRP group number. It'll be standby group 10. We're going to be servicing an IP address of 10.1.1.1, and I'm not going to set the priority here. Do you remember what the default priority is? It's 100. That's going to be less than the 110 that I set on SW2. I'll be fine with the default priority here. I am going to turn on the preempt option. I'll say standby group 10 preempt. And we're done with our initial HSRP configuration. Let's see if it works. Let's go to PC1. And I say PC1, it's really a router acting as a PC. I don't have a routing protocol enabled on this router. I have it pointing to a default gateway of 10.1.1.1, much like a PC would have a default gateway. Let's do a trace route to see which path would I be using to get to this IP address that we're saying is out on the internet, an IP address of 1.1.1.1. We'll say traceroute 1.1.1.1. Which path am I using? Well, you can see my next hop is 10.1.1.2. That's SW2. We are using SW2 as our next hop, which is what we expected. Now the question is, will HSRP really work? If I shut down Fast Ethernet 0/3 on SW2, will the traffic reroute and start using switch SW3? Well, let's try. Let's do an extended ping on PC1. I'll say ping, and I'll give an IP address of 1.1.1.1, and I'll say that my repeat count is a really big number. We will break out of that later, and we can see all the successful pings right now. Let's go over to switch SW2, and let's shut down interface Fast Ethernet 0/3. Let's go into interface configuration mode for Fast Ethernet 0/3, and we're going to do a shutdown, and then very quickly I'm going to go back over to PC1 so that we can see the failover happen. Let's shut down the interface, and you can see we're already starting to drop packets. Instead of the bangs, instead of the exclamation points, we're starting to get the dots. And after about 10 seconds, it was about 10 seconds or so, we've failed back over. Let's break out of this, and let's do another trace route to see if we're now using SW3 to get to 1.1.1.1. Let's do a trace route to 1.1.1.1, and this time notice the next hop. It's 10.1.1.3. That's SW3. HSRP has done its job. HSRP has allowed us to fail over from using SW2 as the active HSRP router to get off of our subnet to switch SW3. Let's do another extended ping, and we will fail back over, but I want to give a debug command on switch SW3 so we can see the failover happening and the output of the debug command. Let's do another extended ping to 1.1.1.1. The repeat count is a really big number that we will break out of later. We'll get the ping started, and then we will go over to switch SW3. And on switch SW3, let's issue a debug command. We can say debug standby, and context-sensitive help shows us some of the different things that we can debug when we're troubleshooting or verifying HSRP. I usually prefer to use this terse option. This displays a limited collection of errors and events and packets. It's normally all I need to see. I'm going to say debug standby terse. We've got that debugging turned on now. Let's go back to switch SW2 and we'll do a no shut. Let's bring this interface back up. We'll do a no shut to bring that back up. Let's go back to PC1 and we should see the ping stop for a moment and then they'll fail back over. They'll start using switch SW2 again. Give that just a few moments. Because we've enabled the preempt option, switch SW2 should be able to take back over, and we see that the pings have stopped after a few seconds. And now we're failing back over, and I would bet that we're now going to be using switch SW2. The failover took a few seconds there. Let's do another trace route. Let's do a trace route 1.1.1.1. Yeah, again, we're using SW2. We failed back over. And let's take a look at the debug output that we have on SW3. I'll do a UAll to stop the debugging. But notice that we received this coup message. Like a governmental coup when somebody takes over the government. Here, we're receiving a coup message from 10.1.1.2, which is SW2, saying, we're taking over. I've got a priority of 110. And as a result of that coup message, the message from SW2 saying, hey, I've got a higher priority for this virtual IP address, notice what we start to do. We start to transition from the active state into the speak state. And then later you see that we go from the speak state to the standby state. And this might be a good time to mention the different states that HSRP has. There is the initial state. That's when an HSRP interface first comes up. There's the listen state. This is where the interface knows its IP address and it's listening for hello messages from other routers. The speak state is when a router is sending hello messages, and it's actively participating in the election of an active or standby router. The standby state, that's when the router is the candidate to become the next active router. It does send periodic hello messages, and of course we have the active state, and that's the router that's actively forwarding packets. Those are the different HSRP states we have. Now let's take a look at a couple of verification commands. Probably my first go-to verification command with HSRP is show standby brief. And here we're on SW3, and you can see that interface fast Ethernet 0/3 is participating in HSRP group 10. We've got a priority of 100, which is the default. And you see this P in this column? This means that we've got the preempt option turned on. Our current state is standby. The current active router is 10.1.1.2, which is SW2. The standby router is us. It's local. And the virtual IP address that we're servicing is 10.1.1.1. We can get a bit more information by saying show standby and giving an interface identifier like fast Ethernet 0/3. This also tells us the interface is participating in group 10. It also tells us that we're currently in the standby state, and it tells us what the virtual IP address is. One other interesting piece of information that we did not get from the previous command, though, is the virtual MAC address that we're using. Here's the MAC address that is associated with 10.1.1.1. Think about this from the perspective of PC1. When it's sending a frame to 10.1.1.1, it needs to know the corresponding MAC address. And it has sent an ARP message saying, hey, can somebody tell me the IP address for 10.1.1.1? And it got this response back saying that here's the MAC address, and this is a virtual MAC address that can be serviced by either SW2 or SW3. And notice the format of this address. The first half of this address is often referred to as the vendor code, 0000.0C. That's one of Cisco's vendor codes. If you see that vendor code followed by 07AC, that's indicating that this is a virtual MAC address for HSRP, specifically for HSRP version 1. I'll show you the version 2 format shortly. And notice the last two hexadecimal digits, 0A. The 0A is the hexadecimal representation of the HSRP group. Think about it. We're in group 10, and we have a 0A here. What is 0A in hex? What is that in decimal? It's a 10. That's the hexadecimal representation of the group. And this output is also showing us our priority, who's the active router, and again, we see that we are the standby router. And let's go over to switch SW2 and give the command show standby brief. And we can see that this router is the active HSRP router. Why? Because we've got a higher priority. Our priority is 110. We see the IP address of the standby router, and that's SW3. Now let's see if we can make this failover happen a bit faster. And by the way, if we start getting into sub-second hello times, Cisco recommends that we use HSRP version 2. Let's see how to do that. Let's go back into interface Fast Ethernet 0/3. And to say that we want to run HSRP version 2, we say standby version 2. And here's how we can adjust the timers. We can say standby 10 timers, and I'm going to give the hello time in milliseconds, and to do that I'm going to say MSEC for milliseconds, and I'll say that my hello time is, let's say, 200 milliseconds. And my hold time, it has to be at least 600 milliseconds, but I'll say that my hold time timer is 900 milliseconds. And let's give a complementary configuration on switch SW3. Let's go into interface Fast Ethernet 0/3, and we'll say that our standby version is 2. And let's set the timers here. We'll say standby 10 timers in milliseconds, 200 for the hello timer, 900 for the hold time timer. By the way, now that we're running HSRP version 2, we've got different leading digits for the virtual MAC address. Check this out. If I do a show standby Fast Ethernet 0/3, we still have that same vendor code of 5 zeros and a C, but look at this. The next few digits are different. We now have 9FF as the next 3 digits, and now, instead of using the last 2 hexadecimal digits to match our HSRP group number, it's the last 3 digits. We could have more group numbers if we wanted. Here it's 00A, still the hexadecimal equivalent of our group number of 10, and we can see that we're now running HSRP version 2. And something else happened when we went to version 2. It doesn't show up in this output, but something I want you to know, you might want to put this in your notes. The multicast address used to send HSRP messages has now changed. HSRP version 1 used the all routers multicast group address, which is 224.0.0.2. HSRP version 2 uses 224.0.0.102. But I would say one of the biggest enhancements with HSRP version 2 is that HSRP version 2 supports IP version 6. Let's see if our convergence time is any better now. Let's go back to PC1 and do another extended ping to an IP address of 1.1.1.1 with a bunch of repetitions. Let's get that ping started, and we'll go back to switch SW2, and let's shut down this interface again. We'll go into interface Fast Ethernet 0/3. Let's do a shutdown, and then we'll very quickly go back to PC1, and let's see how quickly we fail over. Oh, look at that. We only lost 1 ping packet. That convergence time was much, much faster than it was in our previous example. We have dramatically decreased the failover time by using a much lower hello time and a hold time timer. But as a real world tip, you might not want to set the hello time or the hold time timer too low if you're in a network where you might experience delays which might trigger that failover when you really didn't want it to be triggered. If that network is not highly reliable or it's subject to becoming congested, you might want to be careful with having times that are too low. But in our example, it worked out great. Let's fix this with a no shutdown command. And next, let's demonstrate a feature that we talked about earlier called interface tracking. Notice on screen that if switch SW2 were to lose Fast Ethernet 0/1, then it would not be the best choice to get out to the internet. However, SW2 would still be able to send SW3 hello messages, and as a result, it would still be the active router. However, we don't want it to be if that interface going out to the internet goes down. What we can do is tell HSRP to track the state of that interface, and if that interface goes down, we want to decrement our priority. Remember, we've got a priority of 110. We can say, if this interface state goes down, then decrement our priority by 20. That will take us from 110 down to 90, which will be lower than the priority of switch SW3. Here's how we do that. We say standby 10 track, and I'm going to give the interface identifier of Fast Ethernet 0/1. That's the interface that gets us out to the internet, and context-sensitive help shows us that we now put in the decrement value. By how much do I want to decrement? Do I want to reduce my priority if this interface goes down? And I'm going to say 20. And let's confirm our priority right now with a show standby brief command. Currently, our priority is 110. Now, let's shut down this interface. Let's go into interface fast Ethernet 0/1. Let's do a shutdown. Now let's take a look at our priority. We'll do a show standby brief command again. Look at this. Now our priority is 90. And as a result, we're now in the standby state. SW3 is now taken over as the active router because that interface going out to the internet went down. Let's fix this. Let's go into interface fast Ethernet 0/1 and say no shutdown. And while interface tracking is great, there is a more advanced type of tracking. It's called enhanced object tracking. It lets us do things like decrement the priority in the event of a certain network condition, such as a route disappearing from the IP routing table or having a metric of a route exceeding a certain value. Let's see how to set that up. If I do a show run real quick, notice that there is a track statement that got added when I configured interface tracking. I'm going to add another tracking statement now, and it has to be unique, so I'm going to say track 2. But let's go into global configuration mode, and we'll say track 2, and I want to track an IP route of 2.2.2.0 with a 24-bit subnet mask. And by looking at this topology, you can see that I don't have such a network in the topology, but what I did was I created a static route entry. I said route 2.2.2.0/24 to the null 0 interface. So right now that route actually does exist in this routers or in this multi-layer switches routing table. But I want to track that route. And when I track that route, I'm not just looking at its metric value and setting a threshold there. I'm checking for its reachability. Does it or does it not appear in my IP routing table? Here's how I link this to my HSRP process. Let's go back into interface fast Ethernet 0/3 and I'll say standby group 10 track 2 decrement 20. If tracking object number 2, which is checking the reachability of the 2.2.2.0/24 network, if that has a down condition, my priority is going to be decremented by 20. Let's see if it is. Let's do a show standby fast Ethernet 0/3. And you can see that track object 2 is in an up state. However, let's get rid of that route. Let's go in and say no IP route 2.2.2.0, 255, 255, 255.0, null 0, that's where I had it pointing. Let's get rid of that route, and let's see if that does anything to our priority. We just lost that route from the IP routing table. It was a static route. Let's take a look. If I do a show standby fast Ethernet 0/3, we can see that now this state is down. We've decremented our priority by 20, and as a result, we went into the standby state. Let's fix this. Let's go back and put that static route back. I'll say IP route 2.2.2.0, 255.255.255.0, pointing to null 0. That should make that route reappear, and that should make the tracking object go back up, and that should return us to the active state, and indeed it did. And it happened really quickly too. Now at this point, we've seen the basics of HSRP, but there's a security question that comes up now, and that is, what is to prevent somebody from adding a rogue HSRP router to our network, setting the priority really high, and then taking over the active role and causing traffic to flow through their device? Well, at this point, nothing's preventing that from happening. Fortunately, we can, and we probably should, enable authentication for an HSRP group. Let's set that up now between switches SW2 and SW3. HSRP supports a couple of authentication types, plain text and the much preferred MD5 authentication. We probably do not want to be sending plain text authentication across the network because if somebody captures those packets, they can clearly read in plain text what our credential is. Usually it's better to use MD5 because that's going to run a hashing algorithm on the string, and each side runs a hashing algorithm and they compare hash values. And if the hash value is equal, then they have some assurance that the other side, the other device, has the same string. Let's set this up on SW2 by first going into interface configuration mode for fast Ethernet 0/3, and we can say standby, and we give our HSRP group number of 10. And then we say authentication. And you see we could specify text or MD5. We're going to do MD5. And we're going to specify a key string, which we're going to specify here, as opposed to a keychain, which is something that we can configure globally. And we can get really fancy with the keychain. We can have different keys become active at different times, and we can have keys that expire. But here I'm just going to set up a static key string that's going to match on SW3. And I'll say key-string, and I'm going to make this key string $3 CR3 and a capital T. You can see I sort of spelled out secret. Let's go set this up on the other side, because right now I have it set up on one side but not the other. I'm getting an error. I'm getting a bad authentication message. So we need to quickly go over to SW3 and fix it there. Let's go into interface fast Ethernet 0/3, and once again we'll say standby 10, authentication MD5, key-string, and it was $3 CR3 capital T. Hopefully those match. It looks like they did, because we had become active when the authentication parameters did not match. And you see I just now went back into standby. So I think we're good, but let's confirm that. Let's do a show standby fast Ethernet 0/3. And we can see that SW3 is currently in the standby state. That's great. And we can also see that we're using MD5 authentication, and we're using a key string as opposed to a keychain. And to wrap up this video, let's put on our network architect hats for a moment. Let's think about a couple of design issues surrounding HSRP. Number one, let's think about the interaction between HSRP and STP, Spanning Tree Protocol. And also let's think about HSRP load balancing. First, let's think about how HSRP and STP, Spanning Tree Protocol, interact. If we have our switches interconnecting in a redundant fashion where we are running Spanning Tree Protocol, we need to realize that Spanning Tree Protocol has no knowledge of HSRP, and it's possible to have Spanning Tree Protocol blocking a link that is our best path, a link that leads directly to our active HSRP router. And that could cause our traffic to take a suboptimal path to get to that active router. So here's Cisco's best practice recommendation. Cisco says, let's make the layer 3 switch that's acting as the HSRP active router for a VLAN. Let's make that the same switch that's acting as the Spanning Tree Protocol root bridge for that VLAN. That should give traffic in that VLAN an optimal path to get to the HSRP active router. And that leads to our second architectural topic, load balancing with HSRP. We know what per VLAN Spanning Tree Protocol lets us do. It allows us to have different Spanning Tree Protocol instances for different VLANs. Well, similarly, we can have different HSRP groups for different VLANs, and that can give us some load balancing. For example, we might assign interface VLAN 100 to HSRP group 100, and interface VLAN 200 to HSRP group 200, and we do that on a couple of different switches. Then we could have one switch be the active router for HSRP group 100, and the other switch would be the active router for HSRP group 200. And that can let both of these layer 3 switches actively be forwarding traffic instead of having one of them just standing by waiting for the other to fail.